All right. Any questions? I'm sort of taking that as a no. So what we have are some concentric spheres. So it's just a cross section, they're just a bunch of thick shelled spheres. And the question is, what is the electric field at this point, this point, this point, this point, and this point? I need to give some distances here. So that would be 0 meters. We'll just stick with 2 meters, 4 meters, 6 meters, 8 meters, and 10 meters. The 5 coulombs, these are all conducting, they're all metal. And so in this ring right here, I have an excess of 5 coulombs. On this outer ring right here, I have an excess of negative 2 coulombs. So they will distribute however is appropriate. All right, so let's start out with, well, what are the easy ones? If the striped areas are conducting, what do we know without having to do any math whatsoever? Let's make some interesting video there. Oh. That was not an earthquake. That was Ryan. All right, so what do we know? I guess some people are still writing. Okay, so what's going to be true? If these are in electrostatic equilibrium, and enough time has passed for them to be in electrostatic equilibrium, realistically, it's only going to take on the order of a microsecond for it to get into electrostatic equilibrium. What's going to be true?
Net charge is going to be 0?
Not the net charge. The net charge for the whole, what actually, all right, let's start with there. What is the net charge for the entire structure? Somebody go for it.
6 coulombs.
There we go. Yes. All right. So we got 6 coulombs total. Okay, now back to the other question of, it's an electrostatic equilibrium. What's going to be true? All right, tell me one thing. Let's see a number of you look at your notes from the last class.
Excess charges on the surface.
Okay. What else? Someone who can read his own or her own handwriting. This is going to make an incredibly compelling video here. All right, what do you think it says, Luis?
I can't read what this word is, but it says something about E in material is 0 newtons per coulomb.
All right, what does that mean?
Something.
Is there a vector symbol over that E?
Yes.
Okay.
Yes.
What does E with a vector symbol over it?
Electric flux. Electric flux.
No,
The
wrong,
field.
wrong F word.
Field.
Field, yes. Electric flux is a scalar also. The electric field. So the electric field inside the material is 0. So where are we inside the material?
At the
Where?
3 coulombs.
No, as in distances from the center.
We're inside the material at 4 meters and 8 meters.
Yeah. All right. So the question originally was, what is the electric field at each of these points? Well, I know the electric field is here. The electric field here is 0 newtons per coulomb, and here it is 0 newtons per coulomb. So without any math whatsoever, we just meet the statement of the problem that it's an electrostatic equilibrium. We know those 2 electric fields. Boom. We're cruising. Since the electric field is 0 here, what is the charge? And Luis said that the charges are on the surface, so we've got a surface right here. What is the charge on this surface right here? You left a word off. You look like you're about to fall asleep.
Yeah.
But this is physics. You should get pumped up. I guess the excitement of coming over here, you get the adrenaline crash. All right, let's go back to Gauss's law. Of electricity. Since there is one of magnetism also. And so this would be E dot A. Technically, it's the sum of all of them. All right, so if my electric field is 0 here, if I created a Gaussian surface, and you know what, we can be even more stunning in our colors here. Ooh. All right, so there's my Gaussian surface in whatever color that is. It's purple. If I know the electric field everywhere on that surface is 0, what is the total electric flux?
0.
All right. So if the total electric flux is 0, what is the charge within that Gaussian surface?
0.
Yeah, if that's zero, this has to be zero, because epsilon sub naught is definitely not infinite. So therefore, what is the charge on this inner surface? If I know the total charge inside the purple band here is zero.
-3?
Yeah, negative, you said 3. So I got -3 coulombs here, so what is the charge on this surface right here?
Is it gonna have to total to be 5?
Yes.
So 8.
Yeah, so I got 8 coulombs here. We're cruising. I know the electric field at this point is also 0. Using the exact same argument, since the electric field here is everywhere on this second purple surface is 0. Then I know that the total charge within here must be 0. So what is the charge on this surface right here? You look like you want to say it.
Does that equal -10?
Sorry, louder, please.
It's supposed to equal -10.
The whole thing for this surface plus those two surfaces will add up to -2.
Okay.
But just this one right here, yeah, -8. Because the sum of all of those has to add up to 0. And if that's -8 and the whole thing in this band is -2, what would this surface be?
No, 6.
All right, so we know those charges. And then a classic physics question would be to give you the situation. One question would be, what are the charges on each of the surfaces? The other one is, what is the electric field? Well, we got 2 of the electric fields. All right, so let's pick this electric field here. The electric field from this point. Well, we can do the Gaussian surface again. Sure. We didn't have to, but we could. Now, there's a lot of purple lines there, so let's see if we can go for something completely different. Yeah. So I'm creating a Gaussian surface here, a Gaussian sphere more specifically, surrounding that 3 coulomb charge. The radius of that sphere is 2 meters, because that's the point in question, right? So I made it so that it hit that point. Is the total enclosed charge 0? I saw one hit move.
No.
Okay. It is not 0. It is 3 coulombs. So I can come over here using Gauss's law, or we could just use the electric field formula. But I've got my electric field times the area of that sphere. And what is the area of that sphere? What's surface area of a sphere? What's the formula?
Four pi r squared?
Yes.
Yes.
If you mentioned 3, you'll probably think like.
Yeah.
So times 4 pi r squared is equal to my enclosed charge over epsilon sub naught. And so my electric field is going to be my enclosed charge over 4 pi r squared epsilon sub naught, which is 3 coulombs. Coulombs. That's supposed to be a C. 4 pi times 2 squared, 2 meters squared, times epsilon sub naught, which is a constant, which is just good to know. 8.85 times 10 to the 12th coulomb squared per Newton meter squared. On a quiz or test, just look at the top of the first page. Well, actually on a quiz, look at the top of the page. On a test, look at the top of the first page, it'd be there. Or you could say, no test is going to tell me what to do. I'm going to learn this before I walk into the test, so I don't have to look at the top of the first page. That'll show them. And then somebody's gonna work it out on a calculator and come out with some magical number that's just gonna make us all go, ooh. Getting 6 point something, let's see, so. 6.75 times 10 to -10? Say it again?
Negative 15.
-15.
I concur.
Ah, okay. I realize part of my issue. Okay, -12 there. And it's 16, that's 48, 6. Three decimal places that. We get confirmation, the -15. Okay. Units?
Newtons coulombs.
Close.
Newtons times per.
Per. One, you should be able to work out the units from what I have written there. I have a coulombs over meters squared times coulombs over Newton meter squared. The meter squared cancel out. Oh, that's a coulomb squared. That cancels out with that, and I'm left with 1 over coulombs per Newton, which is a Newton per coulomb. Or you should be thinking, oh, electric field, Newtons per coulomb. All right. Now at this point right here at 6 meters, what changes in our work? Okay. So at 6 coulombs, this now becomes 6. What else changes? We got one more thing that's going to change.
The charge.
Yes. What is the charge inside a Gaussian surface that I put right there? Like you mean it,
8 coulombs.
without the question mark.
8 coulombs.
Yep, there we go. Because that's the total charge inside this area right here. So instead of 3/4, we now have 8/36, and it'll be something smaller. And then someone's going to reveal this answer, and we will all be dancing a jig of joy inside us.
(2.00 times 10 to the -15 newtons per coulomb).
And now let's go through this exercise one more time. So now, so we've got the 2, 4, 6, 8, we are now at the 10. I'm now out here. What changes?
Radius.
Okay, so that's now 10.
And aren't we at 0 coulombs now?
No, it's not 0.
It's.
With great confidence and boldness, as if you are right and everyone else is wrong.
I can't. Would it be -8 coulombs?
No,
Would it be -2 coulombs?
no.
Where is the logic?
We got 3 plus -3 plus 8 plus -8 plus 6.
6 coulombs.
Yes, or 3 plus 5 plus -2. Yeah, it's 6.
Right, right.
Because we had 3 coulombs, then I had a ring here with 5 coulombs, then I had another one with -2 coulombs, it adds up to 6. And so it'll be something smaller still.
Four zero.
To times 10 to the -16 newtons per coulomb.
That's right. Actually, the way you said it, I should boldface that. I appreciate the way that all of you are sort of suppressing that desire to just be dancing for joy on the outside, and just keeping it on the inside.
It's tough. It's tough.
Therefore, nothing else from growing up in the 70s, always keep those emotions suppressed. I guess I probably should say, if I learned nothing else from my father, growing up in the 70s, when I was growing up in the 70s. Questions to hear, because I remembered two more things I wanted to get done before I officially put before I declare